Imagine, if you will, a cosmic subway system, a network of tunnels boring through the very fabric of space and time, a shortcut, allowing us to bypass the limitations of light speed, to traverse unimaginable distances in the blink of an eye. This isn't a scene from a science fiction blockbuster, or is it? This is the tantalizing, mind-bending possibility of wormholes. For centuries, humanity has gazed at the stars, dreaming of journeys to distant worlds. Generation after generation has looked up in wonderment. From the ancient mariners navigating by celestial bodies to modern-day astronomers charting the galaxies, the call of the cosmos has always been a siren song, but the sheer scale of the universe presents a daunting challenge. Even at the speed of light traveling to the nearest star system, Alpha Centauri, would take over 4 years. That's 4 years just to reach our closest stellar neighbor. Imagine the decades, centuries, millennia it would take to reach other potentially habitable planets, or to explore the vast and mysterious reaches of our galaxy and beyond. This is where the concept of the wormhole, sometimes called an Einstein-Rosen bridge, ignites the imagination. A hypothetical tunnel through space-time, a shortcut bypassing the conventional laws of physics, offering the potential for instantaneous travel across vast cosmic distances. But are these cosmic shortcuts just the stuff of dreams, the imaginative creations of science fiction writers and filmmakers? Or do they represent a genuine possibility, a hidden feature of the universe waiting to be discovered, or even perhaps, one day, engineered? Consider this. What if we could fold space, bending it like a piece of paper so that two distant points become adjacent? What if we could then pierce through that folded space, creating a tunnel, a bridge allowing passage from one point to another without traversing the intervening distance? It sounds like magic, but the underlying principles are rooted in one of the most revolutionary theories of modern science. If wormholes were proven to exist, if we could somehow harness their power, the implications would be earth-shattering, universe-altering. Imagine explorers venturing to distant galaxies, scientists studying alien life forms firsthand, humanity expanding its reach across the cosmos in ways previously relegated to the realm of fantasy. The colonization of other worlds, the discovery of new resources, the encounter with other civilizations, all within reach. The implications for our understanding of the universe and our place within it would be profound. But the question remains, are wormholes a real possibility? A feature of the universe waiting to be discovered? Or are they merely a captivating illusion, a beguiling concept that will forever remain confined to the pages of science fiction? The answer, as you might suspect, is far from simple, and the journey to unravel this cosmic enigma is just beginning. As captivating as the prospect of cosmic shortcuts may be, to truly grasp the theoretical underpinnings of wormholes, we must journey into the mind of one of history's greatest thinkers, Albert Einstein. It was his groundbreaking general theory of relativity that revolutionized our understanding of gravity and, in doing so, opened the door to the very possibility of these space-time tunnels. But forget what you think you know about gravity. It's not some invisible force tugging at objects, pulling them towards each other. That's the Newtonian view. Einstein gave us something far more profound, a radical shift in perspective. Imagine, if you will, the universe not as a rigid, static arena, but as a dynamic, flexible fabric, a cosmic tapestry woven from space and time. This is space-time, a four-dimensional construct that forms the very foundation of reality. Now, picture a bowling ball placed on a stretched rubber sheet. What happens? The ball creates a dip, a curvature in the fabric. This, in essence, is how gravity works. Massive objects like planets, stars, and black holes warp the space-time around them. They create valleys and curves in this cosmic fabric. Other objects then follow these curves, giving the illusion of being pulled towards the massive object. So, the Earth orbits the Sun not because the Sun is pulling it, but because the Sun is warping the space-time around it, and the Earth is simply following the curve. Consider the Sun, a colossal sphere of burning gas with a diameter of almost 1,400,000 kilometers. Its immense mass creates a significant warp in space-time, dictating the orbits of all the planets in our solar system. Now imagine something far more massive. A supermassive black hole lurking at the center of a galaxy, millions or even billions of times the mass of our Sun. The distortion of space-time around such an object would be almost incomprehensible, a deep, dark abyss where the laws of physics as we know them begin to break down. This flexible geometry of space-time is crucial for grasping how a shortcut, a wormhole, might even be conceivable. If space-time can be bent and curved, could it also be folded? Could two distant points in the universe, light years apart, be brought closer together by warping the fabric of space-time? Could a tunnel, a bridge, then be created to connect these 2 points, allowing for near instantaneous travel across vast cosmic distances? Think of it like this. Imagine an ant crawling on an apple. To get from one side of the apple to the other, the ant has to crawl all the way around the surface. But what if you could bore a hole straight through the apple, creating a shortcut for the ant? That, in essence, is the idea behind a wormhole. It's a tunnel through space-time, a shortcut that bypasses the conventional limitations of distance. But just how could such a tunnel be formed, and what would it take to keep it open? We are only beginning to scratch the surface of those questions. But how do we wrap our minds around something so utterly beyond our everyday experience? How do we make the abstract concrete, the impossible, seemingly possible? That's where analogies and visualizations become essential tools in understanding the wormhole concept. Forget complex equations for a moment and picture this. A flat two-dimensional universe like a sheet of paper. On one side of the sheet is point A, on the other point B. In this two-dimensional world, the only way to travel between A and B is to traverse the surface of the paper a considerable distance. But what if we introduce a third dimension? What if we can now fold that sheet of paper, bringing points A and B closer together, even touching? Then, a tiny being could simply hop from A to B, a journey infinitely shorter than traveling across the original surface. This is the essence of a wormhole. A shortcut through space-time achieved by folding and warping the very fabric of reality. Now, scale that up to our four-dimensional universe. It's harder to visualize, of course, but the principle remains the same. A wormhole, in its most basic form, is a tunnel connecting two distant points in space-time. But it's not just any tunnel. It's a shortcut, a cosmic bypass that allows for travel faster than light, at least in theory. Imagine Earth as one point on that sheet, and a planet orbiting a distant star, say 50 light-years away, as the other. To travel to that planet using conventional means, even at the speed of light, would take 50 years. A human lifetime. But a wormhole, if traversable, could shrink that journey to mere minutes, hours, or days. So what does this theoretical tunnel actually look like? The simplest conceptualization of a wormhole involves two mouths, spherical regions in space-time that act as entrances and exits. Think of them as cosmic portals, shimmering doorways to another place, another time, perhaps even another universe. These mouths are connected by a throat, a tunnel or passageway that bridges the vast distance between them. This throat is the critical element, the key to making the wormhole traversable. But it also presents the greatest challenges, a gauntlet of physics that must be overcome for anything to pass through unscathed. Consider the immense gravitational forces at play near a wormhole mouth. These aren't your everyday garden-variety gravitational pulls. We're talking about forces that could crush a spaceship, rip apart a planet, or even tear apart the very atoms that make up matter itself. The throat of a wormhole is where these forces converge, creating a potential bottleneck that could quickly collapse the entire structure. So how do we keep the throat open? That is one of the biggest mysteries that scientists try to solve every day in different labs around the world. But the journey to understanding wormholes is far from over, and many more questions remain unanswered in the fascinating field of theoretical physics. And yet, even with these visualizations, the concept of a wormhole can feel like grasping smoke. Are they merely mathematical curiosities, elegant solutions to Einstein's equations with no basis in physical reality? Or does nature, in its infinite ingenuity, have a way of realizing these seemingly impossible structures? The seeds of this question were sown back in 1935, not in some far-flung observatory or high-tech laboratory, but within the hallowed halls of academia. Two brilliant minds, Albert Einstein and his colleague Nathan Rosen, were grappling with the implications of general relativity, pushing its boundaries in ways that would forever alter our understanding of space and time. Together, they published a paper that, almost as a byproduct of their primary research, unveiled a startling possibility: the existence of a theoretical bridge connecting two distant points in space-time. This bridge, now known as the Einstein-Rosen bridge, represents the first mathematical description of what we now call a wormhole. It wasn't conceived as a mode of transportation, a cosmic shortcut for interstellar travelers. Rather, it emerged as a peculiar feature of space-time geometry, a kind of topological oddity lurking within the equations of general relativity. Imagine two black holes, not as separate entities, but as interconnected components of a single structure. The Einstein-Rosen bridge proposed that theoretically, these black holes could be linked through a tunnel in space-time, a connection allowing for passage from one to the other. This connection, however, came with a significant caveat. It was deemed non-traversable. According to Einstein and Rosen's calculations, the bridge would pinch off faster than anything could pass through it, rendering it useless as a means of travel. Think of it like a soap bubble, forming momentarily before bursting and disappearing. The Einstein-Rosen bridge, as initially conceived, was similarly ephemeral, a fleeting connection in space-time that existed for only the briefest of instants. Why was it so unstable? The answer lies in the immense gravitational forces at play. The bridge was essentially a tunnel through a region of extreme space-time curvature, and without something to counteract these forces, it would inevitably collapse under its own weight. But even though Einstein and Rosen's original wormhole wasn't considered a viable means of transportation, their theoretical work laid the foundation for future research. It sparked the imaginations of physicists and mathematicians, prompting them to explore the possibility of traversable wormholes, structures that could be navigated safely and efficiently. The Einstein-Rosen bridge, though impassable in its initial form, served as a crucial stepping stone, a catalyst for the ongoing quest to unlock the secrets of space-time and perhaps one day conquer the cosmos. It offers the beginning for our thinking that wormholes are not just plots in science fiction movies, but theoretical and perhaps also physical realities. And what steps were undertaken to get us to that point? Einstein and Rosen's bridge, a tantalizing glimpse into the possibility of wormholes, yet ultimately a dead end. A cosmic cul-de-sac, a fleeting connection that collapses before anything can traverse it. But what if we could somehow prop open that collapsing throat? What if we could stabilize the wormhole, transforming it from a theoretical curiosity into a viable passageway through space-time? This is where the true challenge begins, the Herculean task of engineering a traversable wormhole. The problem, in essence, is gravity. The immense gravitational forces concentrated within the wormhole's throat act like a cosmic vice, squeezing the tunnel shut with relentless force. Ordinary matter, the stuff that makes up planets, stars, and even ourselves, only exacerbates the problem. Its own gravity contributes to the collapse, making the situation even more dire. So what's the solution? It sounds like something out of a science fiction movie. It sounds almost impossible. Negative gravity. But bear with us, because this isn't some crackpot theory. It's a serious proposal rooted in the bizarre and often counterintuitive world of theoretical physics. To keep a wormhole open, we need something that actively pushes outward, something that counteracts the inward pull of gravity. This requires a substance with negative energy density, often referred to as exotic matter. Exotic matter? What exactly is that? Well, that's where things get truly strange. Imagine a substance that has negative mass. Instead of being attracted to gravity, it would be repelled by it. It would float upwards, away from the Earth. It would defy our everyday understanding of how the universe works. Is there anything like that in nature? The short answer is, we don't know for sure. The existence of exotic matter has not yet been definitively proven, and remains in the realm of theoretical physics, for now at least. Think of it like trying to inflate a balloon underwater. The water pressure is constantly pushing inward, trying to collapse the balloon. To keep the balloon inflated, you need to pump air into it, creating an outward pressure that counteracts the water. Exotic matter would act like that air pressure, pushing outwards against the immense gravity, preventing the wormhole's throat from collapsing. But ordinary matter cannot do that. It has positive energy density, and that means it always gravitates, always pulls inward. In fact, the more matter you add, the stronger the gravitational pull becomes, and the faster the wormhole will collapse. So to build a bridge, you need the right materials. Exotic matter is the only one that we know of that could theoretically counteract gravity. How much exotic matter would be required? That depends on the size and shape of the wormhole. But one thing is for sure, it would be an extraordinary amount. Potentially the mass of a planet or even a star, but with a negative sign attached. Could we ever create such a thing? That question brings us to one of the greatest challenges facing modern science. Is exotic matter just a figment of our imagination? A mathematical trick with no basis in physical reality? Or could it be a hidden feature of the universe waiting to be discovered, or even one day engineered? The answer may hold the key to unlocking the secrets of the cosmos and transforming wormholes from science fiction into science fact. The search goes on, and there are more adventures waiting on the way. Imagine holding a ball in your hand and dropping it. It falls to the ground, right? Gravity at work, pulling everything down, holding us all here on Earth. But what if, just what if, you held a ball made of something that defied gravity, something that floated upwards towards the sky? This isn't a scene from a fantasy novel, but a serious question at the heart of wormhole physics. We're talking about exotic matter. This isn't your everyday run-of-the-mill matter, like the stuff that makes up you, me, or even the stars themselves. Exotic matter is a hypothetical substance with properties so bizarre, so counterintuitive, that it challenges our fundamental understanding of the universe. Its key characteristic? Negative energy density. Think of it like this. Normal matter has positive mass, and positive mass creates a gravitational pull. Exotic matter, on the other hand, would have negative mass, creating a gravitational push, a repulsive force that counteracts the normal pull of gravity. It's like anti-gravity in its purest form. Now, why is this so important for wormholes? As we discussed earlier, the throat of a wormhole is under immense gravitational pressure, constantly threatening to collapse in on itself. Ordinary matter would only make this problem worse, but exotic matter with its negative energy density could counteract that pressure, propping open the wormhole's throat and keeping it traversable. It would act like a cosmic scaffolding, preventing the tunnel from collapsing. But what exactly does it mean to have negative energy density? It's a concept that's difficult to wrap our heads around because we simply don't encounter anything like it in our everyday lives. One way to think about it is in terms of pressure. Imagine squeezing a balloon. You're applying positive pressure, forcing the air molecules closer together. Exotic matter, in contrast, would exert negative pressure, pulling outwards, creating a kind of tension in space-time. Now, what properties must this exotic matter possess to stabilize a wormhole? First and foremost, it needs to have a sufficiently large negative energy density to overcome the gravitational forces at play. This could require an amount of exotic matter equivalent to the mass of a planet, or even a star, but with a negative sign. Second, it needs to be stable. It can't just spontaneously decay or dissipate, otherwise the wormhole would quickly collapse. And third, it needs to be controllable. We need to be able to manipulate it, to position it precisely within the wormhole's throat to provide the necessary support. But does this exotic matter actually exist? Is it just a theoretical construct, or is there any evidence that it could be real? This is where the search gets really interesting. While we've never directly observed exotic matter in the wild, there are some tantalizing hints that it might be possible, at least on a microscopic scale. One potential candidate is the Casimir effect, a bizarre phenomenon predicted by quantum field theory. Imagine two parallel metal plates placed in a vacuum. According to classical physics, nothing should happen. But quantum mechanics tells us that even in a vacuum, there's a constant bubbling of virtual particles popping in and out of existence. These particles exert a tiny pressure on the plates, and because the plates restrict the types of virtual particles that can exist between them, the pressure from the outside becomes slightly greater, pushing the plates together. This effect has been measured in laboratories, and it demonstrates that it's possible to create regions of space with negative energy density, albeit on a minuscule scale. However, it is not the stable and abundant source of negative energy density. We need to keep a wormhole open. It's more like a fleeting glimpse of what might be possible. Another possibility lies in the realm of dark energy, the mysterious force that's causing the expansion of the universe to accelerate. While we don't fully understand what dark energy is, one leading theory is that it's a form of exotic matter with negative pressure, pushing the universe outwards. If this is the case, then exotic matter might be far more abundant than we currently realize, pervading the cosmos on a grand scale. Could we one day harness dark energy or some other form of exotic matter to stabilize a wormhole? It's a question that continues to drive theoretical research. However, if nature even permits such strange phenomena on macroscopic scales, it will take significant progress to realize and understand them. Whether it requires breakthroughs in fundamental physics, the discovery of new particles, or the development of entirely new technologies, it's safe to say that our journey is only just beginning. But what if we could? What challenges lie ahead? But even with a theoretical substance capable of pushing back against gravity, the challenge is far from over. Just imagine, you have this carefully constructed tunnel, this shortcut through space-time, held open by the immense repulsive force of exotic matter. But what happens if you let go? What happens if that outward pressure falters, even for a moment? The answer, according to our current understanding of physics, is swift and unforgiving. The wormhole collapses, not gradually, not gracefully, but with a speed that defies comprehension. We are talking about a process that could unfold in a fraction of a second, far faster than anything could possibly traverse the tunnel. Think of it like this. Imagine a skyscraper built on a foundation of sand. It might stand for a while, seemingly stable and secure, but the moment that foundation begins to shift, the entire structure is doomed. The weight of the building, the forces of nature, will conspire to bring it crashing down in a spectacular display of destruction. A wormhole, without constant stabilization, faces a similar fate. The immense gravitational forces at play, the curvature of space-time, all conspire to pinch off the throat, to sever the connection between the two mouths. It is a cosmic game of tug-of-war with gravity pulling inward and exotic matter straining to hold it back. And if gravity wins, the wormhole vanishes, leaving behind nothing but distorted space-time and a lingering sense of what might have been. How quickly would this collapse occur? Physicists have calculated that under certain conditions, the throat of a wormhole could pinch off in less than a millisecond. That is 1,000th of a second. It is an impossibly short amount of time, far too short for even a beam of light to traverse the tunnel. This is why the stability problem is such a formidable hurdle. It is not enough to simply create a wormhole. We must also find a way to keep it open, to maintain the delicate balance between gravity and exotic matter, and to ensure that the tunnel remains traversable for a meaningful amount of time. Visualize it, if you will, using sophisticated computer simulations, watching as the wormhole throat narrows, constricts, and ultimately snaps shut with terrifying speed. The tunnel implodes, space-time ripples, and the dream of instantaneous travel is once again shattered. These simulations paint a stark picture of the challenges involved. They show us just how precarious these structures are, and why the need for exotic matter is not just desirable, but absolutely essential. The required amount of exotic matter to keep the tunnel open needs to be immense. Its gravitational effects should be stronger than gravity as we know it from black holes, and neutron stars to prevent the gravitational collapse. The calculations for a wormhole a meter across would require exotic material with negative mass equal to the mass of Jupiter. With the absence of naturally occurring or human-made exotic material of this scale, it does seem impossible to construct a wormhole as of this moment. But what if we could somehow harness the power of quantum mechanics, the bizarre and often counterintuitive laws that govern the universe at the smallest scales? Could quantum effects provide a natural mechanism for stabilizing wormholes, a way to circumvent the need for vast quantities of exotic matter? This is a question that continues to intrigue physicists. While the details remain murky, the possibility that quantum mechanics might offer a helping hand cannot be ruled out entirely. Perhaps as our understanding of the universe deepens, new discoveries will reveal unforeseen solutions to the stability problem. Maybe we will find new forms of exotic matter, or maybe we will discover entirely new ways to manipulate space-time itself. The quest to conquer the cosmos is not for the faint of heart. It requires ingenuity, perseverance, and an unwavering belief in the power of human curiosity. And the challenges are big, but in that way that humans can overcome them if they believe and work towards a solution. Even with a theoretical plug, that exotic matter, capable of propping open the very fabric of space-time, there remains the looming threat of instant collapse. But what if we could imagine a universe where such a fragile bridge could perhaps come in different shapes, different forms, each with its own set of rules and possibilities? Over the decades, physicists, driven by curiosity and armed with the powerful tools of theoretical physics, have proposed a variety of wormhole classifications, each a unique solution to Einstein's equations, each a testament to the boundless creativity of the human mind. These aren't just idle speculations. These are serious attempts to grapple with the mind-bending physics of wormholes and to understand what forms they might take should they exist. One of the most fundamental distinctions is between static and dynamic wormholes. A static wormhole, as the name suggests, is one that remains fixed in time, its geometry unchanging. It is a stable, unchanging tunnel connecting two distant points in space-time. Think of it as a cosmic highway, always open, always ready for travel. But static wormholes come with a significant challenge. They require a constant and carefully controlled supply of exotic matter to maintain their stability. Any disruption to that supply and the wormhole could quickly collapse. Dynamic wormholes, on the other hand, are far more complex and intriguing. They are wormholes that evolve over time, their geometry changing, their mouths shifting, their very existence potentially fleeting. These are not stable cosmic highways, but rather temporary shortcuts, tunnels that open and close, offering only brief windows of opportunity for travel. Imagine, for instance, a wormhole that pulsates, expanding and contracting like a cosmic heart. One moment it's open and traversable, the next it's closed, impenetrable. While more complex to analyze, dynamic wormholes offer a tantalizing possibility. Perhaps they could form naturally, arising from the chaotic quantum fluctuations of space-time itself, or even from the extreme gravitational environments near black holes. Could these ephemeral tunnels offer a fleeting glimpse into other regions of the universe, or even other universes entirely? Then there are the traversable wormholes, the holy grail of wormhole physics. These are wormholes that, in theory, could be navigated by humans, by spaceships, by anything at all. But what does it take to make a wormhole traversable? As we discussed earlier, the primary challenge is to keep the throat open against the relentless pull of gravity. This requires a sufficient amount of exotic matter, carefully positioned to counteract the inward pressure. But even with exotic matter in place, there are other potential hazards to consider: intense radiation, extreme tidal forces, and the possibility of encountering the exotic matter itself. One of the most well-known examples of a potentially traversable design is the Morris-Thorne wormhole, named after physicists Kip Thorne and Michael Morris. This is a theoretical model of a wormhole that, at least on paper, could be navigated safely by a human traveler. The Morris-Thorne wormhole is characterized by its specific geometry, its relatively gentle tidal forces, and its potential for connecting not just distant points in our own universe, but also different universes entirely. But even the Morris-Thorne wormhole faces significant challenges: the need for vast quantities of exotic matter, the difficulty of controlling its geometry, and the potential for unforeseen instabilities. These varying geometries lead to a lot of different requirements that become the staple of research for each theoretical type. How much exotic material is needed? What physical properties does it need to display? Is it naturally occurring, or can it be engineered? With each question asked, another opens. And yet, despite these challenges, the Morris-Thorne wormhole remains a beacon of hope, a testament to the power of human ingenuity and the enduring allure of the cosmos. Could an incredibly advanced civilization, millions or even billions of years ahead of us, have already mastered the art of wormhole engineering? Could they be using these tunnels to traverse the vast distances of the universe, to explore new worlds, to encounter other civilizations? The possibilities are staggering. This chapter showcases the sheer diversity within the field of wormhole physics research. It highlights the fact that the journey to understanding these cosmic shortcuts is far from over. There are many different paths to explore, many different theories to test, and many different challenges to overcome. But one thing is certain: the quest to unlock the secrets of wormholes will continue to drive scientific discovery for decades to come, maybe even centuries. But if this concept is possible, if somewhere out there a wormhole waits to be discovered, how could it have formed? Does nature have a hand in the construction of these bridges through space-time? That mystery is up next. But if this concept is possible, if somewhere out there a wormhole waits to be discovered, how could it have formed? Does nature have a hand in the construction of these bridges through space-time, or are they solely the domain of highly advanced, perhaps even unimaginable civilizations? The question of whether nature could spontaneously create a wormhole is one of the most intriguing and challenging questions in modern astrophysics. Forget for a moment the mind-boggling engineering feats we've been discussing. Instead, let's consider the raw power of the cosmos. Could nature, in its relentless and often chaotic dance of energy and matter, stumble upon the right conditions to birth a wormhole? The answer, as you might suspect, is shrouded in mystery. But there are some tantalizing possibilities, whispers of hope that nature might indeed be capable of crafting these cosmic shortcuts. Where might we look for such naturally occurring wormholes? Well, the most likely candidates are regions of extreme gravitational stress. Think of the environments near black holes, those cosmic vacuum cleaners that warp space-time to an almost unimaginable degree. Or perhaps the early universe, a time of incredible energy density and quantum fluctuations, when the fabric of space-time itself was being forged. Could a wormhole be born in the heart of a black hole? It's a question that has captivated physicists for decades. Black holes, as we know, are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are the ultimate gravitational sinks, devouring everything that comes too close. But what happens inside a black hole? What lies beyond the event horizon, the point of no return? Our current understanding of physics breaks down, making it impossible to know for sure. Some theories suggest that at the very center of a black hole, there might be a singularity, a point of infinite density, where space-time is infinitely curved. Other theories, however, propose that instead of a singularity, there might be a wormhole, a tunnel connecting the black hole to another region of space-time, perhaps even another universe. Imagine, if you will, a black hole, not as a cosmic dead end, but as a gateway, a portal to another realm. It's a mind-bending concept, one that challenges our fundamental understanding of reality. But how could such a wormhole form? One possibility is that it could arise from the extreme quantum fluctuations that are thought to occur near the singularity. At these scales, space-time itself becomes foamy and uncertain, with virtual particles popping in and out of existence. Could these quantum fluctuations, under the right conditions, create a tiny wormhole, a microscopic tunnel through space-time? And could that tiny wormhole then be amplified, stretched, and stabilized by the immense gravitational forces of the black hole? It's a long shot to be sure, but it's not entirely impossible, and if it were true, it would revolutionize our understanding of black holes and wormholes, transforming them from theoretical curiosities into potentially interconnected phenomena. What if every black hole is connected to a wormhole that opens somewhere else? What if there are as many wormholes as there are black holes? Another possibility is that wormholes could have formed in the very early universe during the inflationary epoch, a period of rapid expansion that occurred shortly after the Big Bang. During inflation, the universe expanded exponentially, doubling in size every 10 to the minus 36 seconds. This incredibly rapid expansion could have stretched and amplified quantum fluctuations, potentially creating primordial wormholes, tiny tunnels through space-time that were then seeded throughout the cosmos. These primordial wormholes, if they exist, would be incredibly small, perhaps only the size of a Planck length, the smallest unit of distance in the universe. But even though they are tiny, they could have significant effects on the universe. They could warp space-time, influence the distribution of matter, and even affect the cosmic microwave background, the afterglow of the Big Bang. So how would we detect a naturally occurring wormhole? That, of course, is the million-dollar question, or perhaps the trillion-dollar question, given the immense scientific and technological resources that would be required. Finding evidence of a wormhole is not going to be easy, but here are certain things that astronomers might look for, telltale signs that could betray the presence of these cosmic shortcuts. One potential signature is gravitational lensing. This occurs when a massive object like a galaxy or a black hole bends the path of light from a more distant object, magnifying and distorting its image. But a wormhole, with its unique space-time geometry, could create a very different type of gravitational lensing effect, one that is distinct from that produced by ordinary matter. Imagine, if you will, looking through a cosmic magnifying glass, but instead of seeing a distorted image of a distant galaxy, you see something completely unexpected, something that doesn't quite fit with our understanding of how the universe should look. That could be a sign that you are looking at a wormhole. Perhaps 2 points are connected, and you are seeing the image of an object on the other side of the universe. Another potential signature is the detection of exotic radiation. If a wormhole is stabilized by exotic matter with negative energy density, that exotic matter could emit radiation with unusual properties, radiation that is unlike anything we have ever seen before. Detecting such radiation would be a smoking gun, strong evidence that exotic matter exists and that it is being used to prop open a wormhole. Astronomers might look for particular gravitational lensing effects. Ordinary gravitational lensing will magnify the galaxy that is behind it as its gravitational field bends the path of the light. However, a wormhole could distort the image of a distant object in such a way that it does not match anything we have seen before. This distortion could result from how wormholes bend the light passing through them. But detecting these faint signals, distinguishing them from the background noise of the universe, is an enormous challenge. It requires incredibly sensitive instruments, sophisticated data analysis techniques, and a healthy dose of luck. The hunt for naturally occurring wormholes is a long shot, a gamble with potentially enormous rewards. Perhaps one day, a new generation of telescopes, orbiting high above the Earth, will catch a glimpse of something truly extraordinary, a flicker of light, a distortion of space-time that reveals the presence of a wormhole. Then what seemed a dream, a plot in a science fiction film, could become a physical reality. But what if nature doesn't provide these cosmic shortcuts? What if we, with our insatiable curiosity and relentless pursuit of the impossible, decided to take matters into our own hands? Could we, or perhaps a civilization far beyond our own, actually build a wormhole? It sounds like the ultimate engineering challenge, a project that would dwarf even the most ambitious feats of human history. Forget building pyramids, skyscrapers, or even space stations. We're talking about manipulating the very fabric of space-time itself. Is it even conceivable? Well, let's consider the sheer scale of the undertaking. We're not talking about digging a tunnel through a mountain or even through a planet. We are talking about creating a tunnel through dimensions. We need to acquire vast amounts of exotic matter with negative energy density. As we discussed before, this stuff doesn't just pop up in our backyards. Even the most optimistic theories suggest that it would require harnessing energies on a scale that is almost unfathomable. Think about the most powerful energy source we know of, a star. Now imagine needing to harness the energy output of an entire star, or perhaps even an entire galaxy, just to create and sustain a wormhole. But the energy requirements are just the beginning. The manipulation of space-time curvature is a feat that defies our current understanding of physics. We're talking about warping the very geometry of the universe, bending space and time to our will. How do we do that? Well, we don't know. Yet. Our current technology barely allows us to scratch the surface of this type of manipulation. We can send a satellite into orbit. We can measure the curvature of space-time around massive objects, but we can't actually control it in any meaningful way. Imagine trying to sculpt a hurricane with your bare hands. That's the scale of the challenge we're facing. We need to develop technologies that can precisely control the gravitational field and manipulate exotic matter to create a stable and traversable wormhole. It would require a level of precision and control that is far beyond anything we can currently achieve. Let's get more specific. To even begin constructing a wormhole, we would first need to find a location where space-time is already somewhat warped. Perhaps near a supermassive black hole where gravity is at its most extreme. Then, we'd need to construct some kind of machine, a colossal space-time manipulator that could focus and amplify that natural curvature. This machine would need to be incredibly powerful, capable of generating gravitational forces that dwarf those of entire stars. Think about the Large Hadron Collider at CERN, the world's largest and most powerful particle accelerator, which is 17 miles in circumference. Now, imagine something 10,000 times bigger. Then, we would need to inject exotic matter into the focused gravitational field, carefully controlling its density and distribution to create the wormhole throat. This would require a level of precision that is almost unimaginable. But here is a secret. The challenges do not stop there. Once the wormhole is constructed, we need to keep it open, stable, and traversable. That requires a constant supply of exotic matter as well as some kind of feedback mechanism to monitor and adjust the wormhole's geometry. Without constant attention, the wormhole will collapse and all our efforts will be for naught. Perhaps we could use artificial intelligence that has an integrated response feedback loop that auto-corrects to the wormhole's ever-changing environment. This AI will need to be able to predict and calculate gravitational fields to apply more negative energy when needed. Of course, even if we could overcome all of these technological hurdles, there would still be the question of safety. What happens if something goes wrong? What happens if the wormhole becomes unstable? What happens if the exotic matter leaks out? The consequences could be catastrophic, potentially destabilizing space-time itself and creating a cascading chain reaction of gravitational anomalies. The slightest miscalculation can have devastating consequences. The idea of building a wormhole is, without a doubt, an engineering nightmare. It challenges our understanding of physics, our technological capabilities, and even our very sanity. It requires resources, expertise, and a level of audacity that is almost beyond comprehension. And yet, despite all of these challenges, the dream of building a wormhole persists. It is a testament to the human spirit, our relentless desire to explore the unknown and to push the boundaries of what is possible. Perhaps one day we will find a way to conquer these challenges and to build our own tunnels through space-time. Until then, it remains a tantalizing, but almost impossibly distant prospect, and it leaves us wondering, how much energy would such a project require? We've talked about exotic matter, about manipulating space-time, about the very real possibility of constructing a wormhole. But let's face it, all of these concepts pale in comparison to the sheer, unadulterated power it would take to actually make it happen. We're not talking about the energy it takes to power your house, or even a city. We're talking about energy on a cosmic scale, energies that would make even the most advanced civilizations of science fiction tremble. Imagine trying to light up the entire planet Earth with a single light bulb and you're still nowhere close. So how much energy are we talking about? That's where things get truly mind-boggling. To create a wormhole, even a tiny one, we would need to bend and warp space-time to an extreme degree, and bending space-time requires energy, a lot of energy. Some theoretical calculations suggest that the energy needed to create a traversable wormhole could be equivalent to the mass energy of a star or even an entire galaxy. Think about it. To create a wormhole, we're essentially fighting against the fundamental forces of the universe, gravity being the biggest one. Gravity is the force that holds planets in orbit, that keeps stars burning, that shapes the very structure of the cosmos. And we're trying to overcome it, to bend it to our will. This requires an amount of energy that is almost incomprehensible to the human mind. Would we need to harness the power of entire stars? Possibly. There are theoretical concepts of Dyson spheres which are hypothetical megastructures that would encompass entire stars to collect their energy. Even if we managed to construct one, it is possible that the amount of energy collected would not be enough to build a wormhole. Perhaps we would have to build a Dyson sphere around a black hole for its gravitational pull alone in order to get the gravitational field needed to begin the construction process. Even with a seemingly impossible task, theoretical scientists are trying to solve these difficult solutions to get to the point that we can at least start to comprehend how we can begin a project of this magnitude. Perhaps we need to tap into something even more fundamental, something that lies at the heart of reality itself. This is where we delve into the realm of Planck-scale physics, the realm of quantum gravity, where the very fabric of space-time is thought to be granular and fluctuating. At the Planck scale, distances are so small, energies are so high, and the rules of physics as we know them begin to break down. Could we somehow manipulate these Planck scale fluctuations to create a wormhole? It's a tantalizing possibility, one that is explored in the most cutting-edge theories of physics, such as string theory and loop quantum gravity. Imagine being able to reach into the fundamental building blocks of the universe and rearrange them like a cosmic architect. But even if we could manipulate Planck-scale physics, the energy requirements would still be staggering. We're talking about energies that are far beyond anything we can currently achieve, energies that might even be beyond anything we can imagine. There are theoretical concepts of harnessing zero-point energy, the energy of empty space itself, but even zero-point energy seems insufficient for wormhole construction. We can measure zero-point energy in a vacuum, but we cannot harness the unlimited potential it possesses. Why is the energy scale so important? Because it puts the feasibility of wormhole construction into stark perspective. It highlights the fact that this is not just a difficult engineering challenge. It's a challenge that pushes the boundaries of what is physically possible. It forces us to confront the fundamental laws of the universe and to question whether there are limits to what we can achieve. Could our understanding of physics be wrong? Is it possible that there are hidden laws, undiscovered forces, that could make wormhole construction easier? It's a question that continues to drive scientific research, pushing us to explore the unknown and to challenge our assumptions. Perhaps one day, a new breakthrough will reveal a pathway to wormhole construction that is far more energy efficient than we currently imagine. But for now, it remains firmly in the realm of speculation, a distant dream that may never be realized. So, with the assumption that we were able to create wormholes to begin with, what perils await inside the wormhole itself? What perils await inside the wormhole itself? Imagine stepping through a shimmering portal, leaving behind the familiar laws of physics and venturing into the unknown. The destination, a distant galaxy, a parallel universe, or perhaps even a different point in time. The journey, instantaneous, or so it seems. But what awaits you in the throat of a wormhole, that tunnel through space-time? Is it a smooth ride, a cosmic subway gliding effortlessly between destinations? Or is it a gauntlet of unimaginable hazards, a trial by physics that could tear you, your spaceship, or even the very atoms that make you up apart? Even if we solve the problems of creation and stabilization, the journey through a wormhole might be a one-way trip straight to oblivion. What are the potential pitfalls that await the intrepid traveler? One of the most significant dangers is intense radiation. The very act of warping space-time, of creating a tunnel through the fabric of reality, could generate tremendous amounts of energy that manifests as high-energy particles, X-rays, and gamma rays. Imagine being bombarded by a cosmic fire hose, a relentless stream of radiation that sears through your spaceship, scrambling electronics, frying biological tissues, and potentially causing irreversible damage to your DNA. How would you shield yourself from such an onslaught? What materials could withstand the intense bombardment of subatomic particles traveling at near light speed? It's a challenge that would require shielding technology far beyond anything we currently possess. Could you use some sort of electromagnetic field, a kind of cosmic force field, to deflect the radiation? Or would you need to encase your spaceship in layers of dense material like lead or depleted uranium to absorb the energy? And even if you could survive the initial blast of radiation, what about the long-term effects? What about the cumulative damage to your body, the increased risk of cancer, the potential for genetic mutations? Then there are the extreme tidal forces, another potential hazard lurking within the wormhole's throat. Tidal forces are the differential gravitational forces that act on an object, stretching it in one direction and squeezing it in another. They are what cause tides on Earth, the rise and fall of the oceans due to the gravitational pull of the moon. Now, imagine tidal forces far more powerful, far more extreme than anything we experience on Earth. Imagine forces that could stretch your spaceship into a long, thin noodle, or crush it into a tiny, insignificant ball. Near a black hole, tidal forces can be so strong that they can rip apart entire stars, a process known as spaghettification. Could similar forces exist within a wormhole? It depends on the size and shape of the wormhole, on the curvature of space-time within the throat. But the potential is certainly there, and it's something that any wormhole traveler would need to take very seriously. How would you protect yourself from such extreme tidal forces? Perhaps you could design your spaceship to be incredibly strong, able to withstand immense pressure and tension. Or maybe you could find a way to manipulate the wormhole's geometry to reduce the tidal forces within the throat. And let's not forget the exotic matter itself, that mysterious substance with negative energy density that is used to prop open the wormhole. As we discussed earlier, exotic matter is a theoretical concept, something that has never been directly observed. What would it be like to interact with exotic matter? What are its properties? What are its potential dangers? Could it be toxic, emitting harmful radiation or releasing dangerous particles? Could it be unstable, prone to sudden explosions or unpredictable behavior? Could it have unforeseen effects on your mind, your body, or even the fabric of space-time itself? The truth is, we simply don't know. We are venturing into the unknown, into a realm where the laws of physics as we understand them may not apply. Maybe there is another hazard, and that is the unknown. No human, no animal, or even robot has ever traveled in a wormhole, and it is impossible to calculate the exact conditions inside the throat. It is too complex to predict all possibilities, and we could be met with unforeseen circumstances. A tear in the metal of the spaceship could cause an instant implosion. The physical conditions inside the wormhole throat are predicted to be unlike anything we have ever experienced. Temperatures could be extreme, ranging from scorching hot to absolute zero. Pressures could be immense, crushing you with the force of 1,000 atmospheres, and the very fabric of space-time could be warped and twisted, creating bizarre optical illusions and distorting your perception of reality. Navigating such an environment would be a challenge, to say the least. You'd need to rely on advanced sensors, sophisticated computer algorithms, and your own wits to survive. Perhaps the journey through a wormhole might be possible in theory, but perilous in practice. It is a high-stakes gamble, a cosmic roulette with potentially fatal consequences. But for those who are willing to take the risk, the rewards could be immeasurable. The chance to explore new worlds, to encounter other civilizations, and to unlock the secrets of the universe. And that is, if we are just considering traveling through space, we haven't even started to scratch the surface of what happens if we can travel through time. Are wormholes able to disrupt the flow of time? And that is, if we are just considering traveling through space, we haven't even started to scratch the surface of what happens if we can travel through time. Are wormholes able to disrupt the flow of time? The very notion that we could manipulate space-time to such an extent that time itself becomes malleable. A river that can be navigated upstream or downstream is enough to send shivers down the spines of even the most seasoned physicists. But the theoretical connection between traversable wormholes and time travel is a serious one, rooted in the elegant equations of Einstein's general theory of relativity. So how could a wormhole function as a time machine? The key lies in manipulating the mouths of the wormhole, creating what are known as closed, time-like curves. Picture this. You have a wormhole, one mouth stationary on Earth, the other placed near a very massive object like a neutron star. Now the trick is to accelerate one of the wormhole mouths to near light speed. According to Einstein's theory, time slows down for objects moving at high velocities, a phenomenon known as time dilation. Think about it like this. You are on a train, traveling at high speed, and you are comparing that to someone that is standing still on the ground. For you on the train, time is moving slower than the person that is standing on the ground. So, as one mouth speeds away, time is moving differently for each mouth of the wormhole. Now, when the mouth that was moving comes back and stops next to the mouth that was on Earth, a difference in time is created between both wormholes. If you were to then jump through the mouth of the wormhole, you could then travel back in time. This time difference, however small, creates a kind of time differential between the two mouths. One mouth is slightly further in the future than the other. Connect these mouths with a wormhole and you have a path from the future to the past. Of course, constructing such a time machine is easier said than done. We would need to overcome all of the challenges associated with creating and stabilizing a wormhole in the first place. We would need to acquire vast amounts of exotic matter, manipulate space-time to an extreme degree, and shield ourselves from the intense radiation and tidal forces within the wormhole's throat. But even if we could overcome all of these challenges, there would still be the problem of causality. Causality is the principle that cause must precede effect. It's a fundamental law of nature, the bedrock upon which our understanding of the universe is built. But time travel throws a wrench into the works, potentially allowing for situations where effects precede their causes. This leads to the infamous paradoxes of time travel. Perhaps the most well-known of these is the grandfather paradox. Imagine traveling back in time and preventing your grandparents from meeting. If they never met, you would never have been born. But if you were never born, you couldn't have traveled back in time to prevent their meeting. It is a logical contradiction, a paradox that seems to defy resolution. Consider another scenario. You travel back in time to give yourself the formula for time travel. So where did this formula come from? It has no origin. It is another logical paradox that has physicists scratching their heads trying to understand time travel and its paradoxes. There are many other time travel paradoxes that exist that challenge our most fundamental concepts about time, causality, and the consistency of the universe. These include, but are not limited to, the predestination paradox, the bootstrap paradox, and many more. These paradoxes raise profound questions about the nature of reality. Does the universe allow for time travel? And if it does, what mechanisms are in place to prevent these kinds of paradoxes from occurring? Are there multiple timelines? Does the universe have self-correcting mechanisms? Do wormholes disrupt the very fabric of time? These are the kind of things that keep scientists engaged and inspire new thought experiments. So how does the universe deal with these potential violations of causality? Is there a cosmic censor, a kind of built-in safeguard that prevents us from altering the past? That is where the real theoretical physics gets interesting. But the universe, it seems, is not so easily fooled. What if the very fabric of reality has built-in safeguards, mechanisms to prevent these paradoxes from unraveling the cosmos? Could the universe be self-healing, capable of patching up any tears in the space-time continuum caused by errant time travelers? This is where things get really speculative, where science flirts with philosophy and the boundaries of our knowledge blur. But don't let that deter you, because the theories are nothing short of mind-blowing. One of the most intriguing ideas is Stephen Hawking's chronology protection conjecture. Hawking, the brilliant theoretical physicist who captivated the world with his insights into black holes and the origins of the universe, proposed that there is a fundamental law of nature that prevents time travel from becoming a reality. He suggested that the universe is inherently resistant to closed time-like curves, the loops in space-time that would allow for time travel. How does the universe enforce this law? Hawking speculated that as you approach a closed time-like curve, as you get closer and closer to being able to travel back in time, quantum effects become increasingly intense. These effects, amplified by the curvature of space-time, could create a barrage of radiation, a kind of cosmic firewall that would either destroy the wormhole or make it impassable. Imagine trying to drive a car through a brick wall at 100 miles per hour. That is the kind of resistance that quantum effects could put in place. The chronology protection conjecture is not a proven theory, but rather a hypothesis, a suggestion based on our current understanding of physics. But it highlights a fundamental question. Does the universe have a vested interest in preserving causality? Does it actively prevent us from messing with the past? Another fascinating concept that attempts to resolve the paradoxes of time travel is the many worlds hypothesis. This idea, which stems from quantum mechanics, suggests that whenever there is a quantum event with multiple possible outcomes, the universe splits into multiple parallel universes, one for each possible outcome. Think about it like this. You flip a coin, and it lands on heads. In our universe, the coin landed on heads. But according to the many worlds hypothesis, there is another universe where the coin landed on tails, and yet another where the coin landed on its side. And so on, for every possible outcome. Now, how does this relate to time travel? Imagine traveling back in time to prevent your grandparents from meeting. According to the many worlds hypothesis, you wouldn't be changing your past. Instead, you would be creating a new branch of reality, a parallel universe where you were never born. In your original universe, you would still exist and everything would remain the same. You would have simply created a new timeline, a new branch on the tree of reality. Imagine a tree with infinite branches. Each branch represents a different reality, a different possible outcome. Time travel, according to this view, doesn't alter the past. It simply shifts you to a different branch of the tree. It is a mind-bending concept, one that suggests that there are infinite versions of ourselves living out different lives in different universes. This approach neatly sidesteps the grandfather paradox, because you are not actually changing your own past. You are simply creating a new reality where the past is different. It's like writing a new chapter in a book, rather than rewriting a chapter that has already been written. Both the chronology protection conjecture and the many worlds hypothesis are just two of the many ideas that physicists are exploring to grapple with the paradoxes of time travel. These safeguard concepts touch on time, dimensions, and other things that we do not yet understand. These ideas are challenging and complex. Perhaps, as our understanding of the universe deepens, we will discover even more elegant and profound solutions to these paradoxes. Perhaps we will find that time travel is not only possible, but also safe and consistent with the laws of nature. Or perhaps we will find that the universe has built-in mechanisms to prevent us from tampering with time, preserving the sanctity of cause and effect. But even if time travel remains a distant dream, the quest to understand it will continue to drive scientific discovery, pushing us to explore the boundaries of our knowledge and to question the fundamental nature of reality. And even if time travel is impossible, the journey to understand why is well worth taking. So with so many universes, can we even think about interuniversal travel? But even if we could somehow navigate the treacherous waters of time travel, even if we could sidestep the paradoxes and avoid unraveling the fabric of causality, there remains an even more audacious, more mind-bending possibility. What if wormholes could connect not just distant points in our own universe, not just different points in time, but entirely different universes altogether? Is this even within the realm of scientific possibility, or does it belong solely to the realm of science fiction? Could our universe be just one of many, an island in a vast cosmic archipelago of alternate realities? The idea of a multiverse, a collection of potentially infinite universes, has been gaining traction in theoretical physics for decades. It's a concept that arises from various theoretical frameworks, from quantum mechanics to string theory, each offering its own unique vision of what the multiverse might look like. Imagine a cosmic bubble bath, each bubble representing a separate universe, each with its own unique laws of physics, its own constants of nature, its own history and destiny. Some of these universes might be very similar to our own, virtually indistinguishable from the world we know. Others might be radically different, governed by entirely different rules, populated by entirely different forms of matter and energy. Could a wormhole be a bridge between these bubble universes, a tunnel connecting our reality to another? It is an interesting thought experiment, and it makes one wonder how this is at all possible. What theoretical frameworks might allow for such interuniversal connections? One possibility lies in the realm of quantum mechanics. As we discussed earlier, quantum mechanics suggests that reality is not fixed and definite, but rather probabilistic and uncertain. At the quantum level, particles can exist in multiple states at once, a phenomenon known as superposition. And they can be linked together in a strange and mysterious way, a phenomenon known as quantum entanglement. Could wormholes somehow exploit these quantum effects to create connections between different universes? Could entangled particles in our universe be linked to entangled particles in another universe through a wormhole, creating a kind of quantum bridge? It's a speculative idea, to be sure, but it's not entirely out of the question. The universe at its deepest levels is far stranger and more mysterious than we can possibly imagine. Another possibility lies in the realm of string theory, a theoretical framework that attempts to unify all the forces of nature into a single, elegant description. String theory suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings, and that these strings can vibrate in different ways, giving rise to different particles and forces. String theory also suggests that our universe may have more dimensions than the 3 spatial dimensions and one time dimension that we experience. In fact, some versions of string theory propose that there may be as many as 11 dimensions. Could these extra dimensions provide a pathway between different universes? Could wormholes act as tunnels through these higher dimensional spaces, connecting our universe to other universes that are located just beyond our reach? Imagine, for a moment, that our universe is like a sheet of paper, and that there are other sheets of paper stacked on top of and below it. These other sheets represent other universes, each with its own unique properties. Now, imagine that you can fold the sheet of paper, bringing 2 distant points together. That's what a wormhole could do, connecting our universe to another universe through a shortcut in higher dimensional space. Of course, interuniversal travel is fraught with peril. Even if we could somehow create a wormhole that connects to another universe, what would we find on the other side? Would it be a paradise, a utopian world teeming with life and wonder? Or would it be a hellscape, a hostile and unforgiving environment where we could not possibly survive? What if the laws of physics in that other universe were different, making it impossible for our technology to function or for our bodies to survive? What if there were intelligent beings in that other universe, beings that were far more advanced than us and that viewed us as a threat? Would they welcome us with open arms, or would they try to destroy us? The possibilities are endless and the risks are immense. Interuniversal travel is not for the faint of heart. It is a journey into the unknown, a leap into the abyss. Could a wormhole be more than just a shortcut through space-time? Could it be a gateway to infinite possibilities? As we continue to explore the mysteries of the cosmos, as we delve deeper into the bizarre and often counterintuitive world of theoretical physics, we may one day find the answer to these questions. And when we do, the implications will be staggering. It pushes the boundaries of what wormholes might represent, and we must consider what evidence we may find. So, how would you go about spotting one of these elusive space-time shortcuts? Even if we could somehow build these cosmic subway stations, these interdimensional portals, how would we know they were even there? How would we differentiate a wormhole from, say, a black hole or some other bizarre cosmic phenomenon that our universe might conjure up? The search for wormholes is not like searching for a lost sock in your dryer. It's like searching for a single grain of sand on every beach on planet Earth, blindfolded, at night. But hope is not lost. The key lies in identifying unique observational signatures, telltale signs that would betray the presence of a wormhole to a watchful astronomer. Imagine yourself as a cosmic detective, armed with the most advanced telescopes and analytical tools, scouring the heavens for clues. What would you look for? One of the most promising signatures is gravitational lensing, the bending of light by massive objects. As we discussed earlier, massive objects warp space-time, causing light to bend around them like water flowing around a rock. This bending of light can magnify and distort the images of distant objects, creating spectacular visual effects. Black holes can cause the same visual effect. But wormholes, with their unique space-time geometry, could produce gravitational lensing patterns that are distinct from those created by black holes or other more conventional objects. Think of it as a cosmic fingerprint, a unique distortion of light that only a wormhole could create. What would this fingerprint look like? Well, it depends on the size and shape of the wormhole, on the distribution of matter and energy within it, and on the relative positions of the wormhole, the background source of light, and the observer, which in our case would be an astronomer here on Earth. But in general, a wormhole could produce multiple images of the same distant object, creating a kind of cosmic hall of mirrors. These images might be magnified, distorted, or even inverted, creating a visual spectacle that would be unlike anything we have ever seen before. Astronomers would have to differentiate the distortions, which can be difficult to discern. But scientists may also discover unique radiation emission patterns, which would allow the identification of a wormhole. Imagine a distant quasar, a supermassive black hole at the center of a galaxy, spewing out a torrent of light and energy. If there were a wormhole between us and the quasar, the light from the quasar would be bent and distorted as it passed through the wormhole, creating a unique lensing pattern. This pattern would be different from the lensing pattern created by a black hole or a galaxy, allowing us to identify the wormhole. Astronomers might also look for certain radiation emissions. But there is a problem, as they are often mistaken for black holes, another celestial phenomenon. Differentiating between black holes and wormholes is crucial. Imagine confusing a doorway for a dead end, or mistaking a bridge for a bottomless pit. Black holes, as we know, are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They are cosmic vacuum cleaners, devouring everything that comes too close. They also have a unique gravitational pull that sucks in gas. This gas then becomes superheated and will emit radiation. Wormholes, on the other hand, are tunnels through space-time, connecting two distant points in the universe. They are cosmic shortcuts, allowing for travel between far-flung locations. A wormhole lacks an event horizon, the point of no return that defines a black hole. That means that in theory, you could shine a light on a wormhole. The light from a black hole will never escape its gravitational pull. While they might be linked in some theories, how might they differ from an astronomical perspective? If we were to approach a wormhole mouth, we wouldn't expect to see the same kind of dramatic visual effects that we would see near a black hole. There wouldn't be an event horizon, no point of no return. Instead, we might see a subtle distortion of space-time, a slight bending of light, or a faint gravitational lensing effect. The question then becomes, how do we spot the differences? One way is to analyze the gravitational lensing patterns, the way that light is bent and distorted by the object's gravity. Black holes create a very specific type of lensing pattern, a dark shadow surrounded by a ring of light. This shadow is caused by the black hole's event horizon, the boundary beyond which nothing can escape. Wormholes, on the other hand, could create a very different type of lensing pattern, one that is more complex and less symmetrical. They might create multiple images of the same distant object, or they might distort the images in unusual ways. By carefully analyzing these lensing patterns, astronomers could potentially distinguish between black holes and wormholes. Another way to tell the difference is to look for signs of exotic matter, the hypothetical substance with negative energy density that is needed to prop open a wormhole. If a wormhole is stabilized by exotic matter, that exotic matter might emit radiation with unusual properties, radiation that is unlike anything we have ever seen before. Astronomers could also use gravitational waves, ripples in the fabric of spacetime, to search for wormholes. When massive objects accelerate, they create gravitational waves that propagate through the universe like ripples in a pond. Black holes are known to generate strong gravitational waves when they collide or merge. And wormholes, with their unique space-time geometry, could also generate gravitational waves, but with a different signature. Perhaps there are unique gravitational wave signals unique to wormholes. By analyzing these waves, astronomers could potentially detect the presence of wormholes and distinguish them from black holes or other cosmic objects. The search for wormholes is a daunting task, but it's one that is driven by our insatiable curiosity and our relentless pursuit of the unknown. It requires ingenuity, perseverance, and a willingness to challenge our assumptions about the universe. Perhaps, in the grand scheme of the cosmos, there are many that exist at the smallest scales. Can these be amplified? But perhaps, in the grand scheme of the cosmos, there are many that exist at the smallest scales. Can these be amplified? What if the universe is riddled with them, too small to detect with our current technology, constantly forming and collapsing like bubbles in a cosmic foam? Now, the puzzle becomes even more intriguing. How do we tell the difference between a dark, devouring abyss and a potentially traversable tunnel. Black holes, with their insatiable hunger, and wormholes, with their promise of cosmic shortcuts, might seem like polar opposites, but their gravitational signatures can be deceptively similar. Imagine trying to distinguish between a powerful vacuum cleaner and a doorway that leads to another room, based solely on the sound of the airflow. So, what are the crucial distinctions that astronomers can look for? What are the telltale signs that would reveal the true nature of these enigmatic objects? One key difference lies in the event horizon. A black hole, as we know, is defined by its event horizon, a point of no return beyond which nothing, not even light, can escape. It's a one-way street, a cosmic trap from which there is no escape. Wormholes, on the other hand, lack an event horizon. They are traversable, at least in theory, allowing for passage in both directions. This fundamental difference has profound implications for their observational appearances. Picture this. You are observing a black hole from a safe distance. You see a dark, empty void surrounded by a ring of light. This ring is formed by photons, particles of light, that are orbiting the black hole trapped in its powerful gravitational field. But the black hole itself remains invisible, hidden behind its event horizon. It is as if the universe has a black hole-shaped sensor bar that cannot be lifted. Now imagine observing a wormhole. You might see a similar distortion of space-time, a bending of light, but you would not see an event horizon. Instead, you might see a glimpse of something on the other side of the wormhole, a distorted image of a distant galaxy, or perhaps even another universe. It would be like looking through a cosmic peephole, a window into another part of reality. But distinguishing between these two scenarios can be tricky. Black holes can also create complex lensing patterns, and wormholes might be obscured by dust and gas, making it difficult to see what lies on the other side. And so, astronomers must rely on other clues, other pieces of the puzzle to unravel the true nature of these objects. One promising avenue of research involves studying the accretion disks that often form around black holes. As matter spirals inward toward a black hole, it heats up and emits intense radiation, creating a swirling disk of light and energy. The properties of this accretion disk, its temperature, its density, its spectral signature, can provide valuable information about the black hole itself. Could wormholes also have accretion disks? It's a question that is still being debated by physicists. If they did, the properties of those disks might be very different from those surrounding black holes, perhaps exhibiting unusual spectral features or temperature gradients. Imagine analyzing the light from a distant object, carefully dissecting its spectrum, its rainbow of colors. If you saw a spectral signature that didn't quite fit with what you would expect from a black hole, or from any other known object, it could be a sign that you were looking at a wormhole. Another key difference between black holes and wormholes lies in their stability. Black holes are relatively stable objects, their properties changing slowly over time. Wormholes, on the other hand, are thought to be inherently unstable, prone to collapsing or pinching off. This instability could manifest itself in various ways, perhaps through fluctuations in the gravitational field, or through bursts of radiation. Astronomers could also use gravitational waves to search for wormholes, in hopes of detecting specific gravitational waves that are unique to wormholes. Imagine the universe as a vast ocean, and gravitational waves as ripples on the surface. Black hole mergers, collisions between two black holes, create powerful gravitational waves that can be detected by observatories here on Earth. Could wormholes also generate gravitational waves? Theoretically, yes. The warping of space-time associated with a wormhole could create ripples in the fabric of reality. But the gravitational waves from wormholes might be very different from those generated by black holes, perhaps exhibiting unusual frequencies or polarizations. Detecting these subtle differences would require incredibly sensitive instruments and sophisticated data analysis techniques. But the potential reward is enormous. the confirmation of a wormhole, a cosmic shortcut that could revolutionize our understanding of the universe. Perhaps the universe is a cosmic puzzle box, filled with hidden compartments and secret passages. And black holes and wormholes are just two of the many mysteries that await us, waiting to be unlocked, waiting to be explored. The answers are out there somewhere, and scientists across the globe keep on looking, because what would happen if they finally found one? What if the vastness of space, the seemingly endless emptiness between galaxies, is not so empty after all? What if, lurking beneath the surface of our reality, there exists a hidden world, a seething foam of quantum activity where wormholes are not exotic anomalies, but rather the norm? We are about to shrink down, not just to the size of an atom, but to the unimaginably small Planck scale, the very limit of what our current understanding of physics can describe. Here, quantum mechanics meets gravity, and the familiar rules of our everyday world dissolve into a haze of uncertainty. It was the brilliant physicist John Wheeler who first proposed the concept of quantum foam, a mind-bending vision of space-time at its most fundamental level. Wheeler, a mentor to such luminaries as Richard Feynman and Kip Thorne, imagined that at the Planck scale, space-time is not smooth and continuous, but rather a chaotic and dynamic arena, riddled with constantly forming and collapsing microscopic wormholes. These aren't the large, traversable wormholes that we've been discussing, the cosmic shortcuts that could whisk us to distant galaxies. These are far smaller, fleeting tunnels that wink in and out of existence on timescales far shorter than anything we can directly observe. Think of it like this. Imagine zooming in on a calm ocean surface until you can see the individual water molecules. At that scale, the ocean is no longer smooth, but rather a turbulent, churning mass of activity. Quantum foam is spacetime's equivalent of that molecular-level chaos. Could these tiny tunnels, these fleeting connections between distant points in spacetime, have any macroscopic consequences? Could they somehow be amplified, scaled up, to create wormholes that we could actually use? It sounds like science fiction, but some physicists believe that it is a possibility worth exploring. One intriguing idea is that these microscopic wormholes could affect the behavior of light. As light travels through space-time, it might encounter these tiny tunnels, briefly entering and exiting them, causing it to be slightly scattered or delayed. This scattering could, in theory, be detectable, providing a way to probe the quantum foam and to search for evidence of these microscopic wormholes. It is as if the universe is winking at us, constantly giving clues to its reality. Imagine shining a laser beam through empty space and carefully measuring the arrival time of the photons. If the photons are delayed or scattered in a way that cannot be explained by any known phenomenon, it could be evidence that they have encountered quantum foam. It is like searching for the faintest flicker of light in the vast darkness of space. Another possibility is that these microscopic wormholes could play a role in the creation of larger, more stable wormholes. Perhaps under the right conditions, a collection of these tiny tunnels could coalesce, merging together to form a wormhole that is large enough to be traversable. It would be like individual drops of water coming together to form a mighty ocean. Of course, this is all highly speculative. We don't even know for sure if quantum foam actually exists, but the possibility that space-time itself is riddled with microscopic wormholes is a tantalizing one, a reminder that the universe is far stranger and more wonderful than we can possibly imagine. And this brings us to a critical juncture, the connection between the very small and the cosmic structures. Could these quantum fluctuations that happen at the smallest possible scale actually influence the bigger picture of the universe? And with that, we open the door to a new area of exploration, a topic that will truly test the limits of our understanding of the universe. But now, with the potential for pathways that connect across the vastness of the cosmos, or perhaps even between universes looming before us, it begs the question, where did this fascination with wormholes truly begin? It wasn't in a dusty laboratory, nor amongst chalkboards covered in complex equations. It began instead in the fertile ground of our imaginations, in the worlds crafted by science fiction. For decades, wormholes have been a staple of science fiction literature, film, and television, shaping our perception of what might be possible, blurring the lines between scientific speculation and fantastical storytelling. How many of us first encountered the concept not in a physics textbook, but on the screen aboard a starship hurtling through a shimmering vortex? Consider the impact of Star Trek: Deep Space Nine. For 7 seasons, viewers were transported to the edge of known space, to a station orbiting a stable wormhole that served as a gateway to the Gamma Quadrant. This wasn't just a plot device. It was a fundamental element of the show's narrative, driving exploration, conflict, and the encounter with alien civilizations vastly different from our own. The wormhole became a character in itself, a source of wonder, mystery, and even spiritual significance for the Bajoran people who revered it as the celestial temple. Did Deep Space Nine spark a sense of cosmic possibility in a generation of viewers, planting the seed of curiosity about wormholes in their minds? Then there's Stargate, a franchise built entirely around the concept of a network of wormhole devices scattered throughout the galaxy and beyond. These stargates, remnants of an ancient civilization, allowed for instantaneous travel to distant worlds, connecting disparate cultures and sparking interstellar conflict on an epic scale. Stargate presented wormholes as readily accessible, almost commonplace, tools for exploration and adventure. It fostered a sense of boundless possibility, suggesting that the universe was far more interconnected than we might have imagined. What does this portrayal of wormholes as convenient portals say about our desire to overcome the limitations of distance and time? And of course, we can't forget Contact, Carl Sagan's novel and subsequent film, a story that grappled with the scientific and philosophical implications of encountering an alien civilization. In Contact, wormhole travel is depicted as a disorienting, almost psychedelic experience, a journey through the very fabric of spacetime. The film consulted with physicist Kip Thorne to depict the wormhole travel as scientifically accurate as possible. What makes Contact stand out is its attempt to ground the concept of wormholes in real physics, to explore the potential dangers and the profound impact on human consciousness. It prompted audiences to consider not just how we might travel through a wormhole, but what it would mean to do so. These fictional portrayals and countless others have shaped our collective imagination, influencing public perception of wormholes in profound ways. They've popularized the idea, making it accessible and engaging for audiences who might not otherwise be interested in theoretical physics. But they've also taken creative liberties, simplifying complex concepts and embellishing the reality to create compelling stories. What are some of the common tropes, the recurring themes and motifs that we see in these fictional portrayals of wormholes? One is the idea of instantaneous travel, the ability to traverse vast distances in the blink of an eye. This trope taps into our deep-seated desire to overcome the limitations of space and time, to explore the universe without being constrained by the speed of light. Another common trope is the use of wormholes as gateways to other dimensions or universes. This trope speaks to our fascination with the unknown, our longing to explore the uncharted territories of reality. It also raises profound questions about the nature of existence, about whether our universe is unique or just one of many. Perhaps the most pervasive trope is the notion of wormholes as unpredictable and dangerous phenomena. This trope reflects our inherent fear of the unknown, our anxiety about tampering with forces that we don't fully understand. It also serves as a cautionary tale, reminding us that even the most promising technologies can have unintended consequences. Do these fictional portrayals inspire scientific curiosity, or do they create unrealistic expectations? Do they fuel our desire to explore the cosmos, or do they instill fear about the potential dangers that await us? Maybe it is a mixture of both. Perhaps the enduring allure of wormholes in science fiction lies in their ability to tap into our deepest hopes and fears, our longing for discovery, and our apprehension about the unknown. These stories help us to ask ourselves questions of the universe and ponder ideas that may otherwise seem impossible. As the journey to understanding the physics behind wormholes continues, another group explores the narrative ideas behind them and the questions that they pose. But what happens when the skeptics weigh in? But what happens when a scientist, someone deeply entrenched in the rigors of factual accuracy and theoretical possibility, decides to tell a story? Can scientific rigor and narrative artistry coexist? The answer, it seems, is a resounding yes, and perhaps no example illuminates this more brightly than Carl Sagan's Contact. Was it just another science fiction film, or was it an attempt to portray what that first contact with another civilization might look like? Contact is more than just a story about wormhole travel. It is a carefully constructed vision, guided by scientific principles, exploring the potential implications of such a monumental discovery. But what is more fascinating is how Sagan chose to depict wormholes in Contact, and how that has been influenced by the theoretical physicist Kip Thorne. Sagan, a man deeply committed to scientific accuracy and communication, recognized the need for a scientific compass to guide the narrative. He sought out Kip Thorne, a renowned theoretical physicist, and challenged him to not just critique the concept, but to shape it, to ensure that the wormhole travel depicted in Contact was at least theoretically plausible. This wasn't just about adding a veneer of science to a fictional story. It was about truly exploring the possibilities, about pushing the boundaries of what we know and what we can imagine, while staying grounded in the known laws of the cosmos. Thorne accepted the challenge, embarking on a journey that would blur the lines between science and fiction. He delved into the intricacies of wormhole physics, exploring the conditions necessary for traversability, the potential dangers, and the very real limitations that might constrain such a journey. Thorne's consultation became an essential part of Contact's DNA, an infusion of scientific realism that elevated the story beyond the realm of pure fantasy. For example, how do you portray the experience of traveling through a wormhole? How do you capture the disorienting sensation of bending space-time, of traversing vast distances in an instant? Thorne's insights helped shape the visual representation of the wormhole journey in Contact, resulting in a sequence that is both awe-inspiring and scientifically informed. Instead of simply depicting a swirling vortex, the film attempted to portray the effects of extreme gravity, the warping of light, and the potential for multiple views of distant objects. It was a conscious effort to avoid the typical science fiction clichés and to present a more grounded, more realistic depiction of wormhole travel. What do you think of a collaboration between scientists and storytellers, and how the depictions in film will influence scientific discovery? Thorne's involvement also extended to the depiction of the wormhole itself, suggesting the use of exotic matter to keep the tunnel open and stable. This wasn't just a plot device, it was a reflection of the real scientific challenges associated with wormhole travel. The film didn't shy away from the complexities, nor did it sugarcoat the difficulties. It presented wormhole travel as a daunting undertaking, a journey fraught with peril, requiring immense resources, advanced technology, and a willingness to confront the unknown. Why did Sagan and Thorne push for the depiction of wormhole travel to be a dangerous, realistic concept? Think about the scene where Ellie Arroway, the protagonist, enters the wormhole. The experience is not smooth or effortless. It is a chaotic, disorienting, and even frightening journey, filled with flashing lights, distorted images, and a sense of being tossed around like a rag doll. This wasn't just a visual spectacle. It was an attempt to convey the true intensity of such a journey, the potential for physical and psychological trauma. It was a journey so awe-inspiring that it left the protagonist speechless, but forever changed. Is this scientist-storyteller collaboration something unique? Perhaps what can be said is that Contact stands as a testament to the power of collaboration between scientists and storytellers, a reminder that science can inform fiction and that fiction can inspire science. It demonstrated how rigorous scientific principles can be woven into a compelling narrative, creating a story that is both entertaining and thought-provoking, and that kind of collaboration is still ongoing in the world of astrophysics. But before the scientists and storytellers can embark on their work, there must first be skeptics who question all of the logic of this science fiction dream. But before the scientists and storytellers can embark on their work, there must first be skeptics who question all of the logic of this science fiction dream. And nowhere is this more evident than in the visual spectacle of Christopher Nolan's Interstellar. Could a movie, a piece of entertainment, actually advance our understanding of the universe, or is it simply a distraction? Interstellar dares to ask this question, presenting audiences with a wormhole not as a convenient plot device, but as a central, almost character-like element in a story about humanity's desperate search for a new home. But how did Nolan, with the help of Kip Thorne, attempt to portray the journey through the wormhole and the effects of warped space-time in a way that was both scientifically plausible and visually stunning? Can a film built on spectacle truly inform? The answer, it seems, lies in the meticulous attention to detail, the willingness to consult with experts, and the dedication to grounding the science in real physics. This wasn't just about creating a visually impressive sequence. It was about exploring the potential consequences of traveling through a wormhole, about depicting the effects of extreme gravity, time dilation, and the disorientation of navigating a tunnel through space-time. Did the filmmakers succeed in striking a balance between scientific accuracy and cinematic storytelling? Interstellar's wormhole sequence stands as a case study in the power of visual effects to communicate complex scientific concepts. How else could one visualize the warping of space, the bending of light, and the strange geometry of a wormhole's interior? The film didn't simply show us a tunnel. It showed us a universe turned inside out, a kaleidoscope of colors and distortions, a visual representation of the mind-bending physics at play. But the film went beyond just visual spectacle. It attempted to explore the subjective experience of traveling through a wormhole, the disorientation, the sense of being untethered from reality, the potential for psychological and emotional impact. Think about Cooper's journey through the wormhole near Saturn. What are the most scientifically sound elements? Is it possible that wormholes are the gateway to another dimension? Interstellar wasn't just about what Cooper saw, but how he felt, how his perceptions were challenged, and how his understanding of the universe was transformed. The film was a thought experiment, presenting the audience with a plausible vision of what wormhole travel might actually entail. This journey, while visually impressive, has been seen as scientifically accurate as well. However, the film needed to add a level of artistic creativity in order to tell the story in a way that would make it captivating for the audience. As Nolan has stated in his interviews, there is always a fine balance in creating something that is accurate and something that is creative and entertaining. It is this collaboration that has scientists and Hollywood knocking at each other's doors. The partnership to find common ground between storytelling and scientific facts has made Interstellar one of the most respected films on space exploration in cinema history. This movie has inspired a new generation of scientists who cite the film as the reason why they chose to explore astrophysics. Without these collaborations, what would inspire the next generation? Would they even be interested in exploring the stars without the visual spectacles to ignite their imaginations? What kind of questions will they ask? Are there other dimensions? So while the dream continues, another very important ingredient is needed. What about the skeptics? How can we analyze the reality and possibilities of these theoretical physics while also having an open mind? And so, while the dream continues, another very important ingredient is needed, a dose of healthy skepticism. For every visionary pushing the boundaries of theoretical physics, there's a chorus of voices urging caution, demanding empirical evidence, and pointing out the colossal hurdles that stand in the way of wormhole travel. Why, despite decades of research and countless hours of speculation, do wormholes remain stubbornly theoretical? What are the most compelling arguments against their physical reality, or even their practical possibility? Let's step into the skeptic's corner and examine the cold, hard facts that keep wormholes firmly in the realm of science fiction. The first and perhaps most significant stumbling block is exotic matter. We've talked about its crucial role in propping open a wormhole, counteracting the relentless pull of gravity. But the truth is, exotic matter remains entirely hypothetical. Despite decades of searching, scientists have never definitively detected a substance with negative mass or negative energy density in the quantities needed. Is it possible that exotic matter simply doesn't exist in the way that we need it to? Or perhaps it exists only in fleeting microscopic forms, far too small to be harnessed for wormhole construction. The lack of a verifiable exotic material remains a glaring issue in its plausibility. But let's, for a moment, be wildly optimistic and assume that scientists were to discover exotic matter tomorrow, a stable, controllable substance with all the properties we need. The challenges would still be far from over. There is, in fact, the staggering energy requirements. Constructing a wormhole, even a relatively small one, would require manipulating space-time on a scale that is almost beyond comprehension. We are talking about energies equivalent to the mass of a star, or perhaps even an entire galaxy. Where would we get such energy? How would we harness it? And how would we control it with the precision needed to sculpt a tunnel through space-time? The physics alone seem impossible to solve in the short term. And then there's the small matter of stability. Even if we could create a wormhole and prop it open with exotic matter, how would we keep it from collapsing? Wormholes are notoriously unstable structures, prone to pinching off and disappearing in a fraction of a second. How could we ensure that our wormhole remains open long enough for a spaceship to pass through, let alone for repeated trips? It is a daunting task that seems to defy the laws of physics. Without constant stabilization, the wormhole would likely pinch off faster than anything could pass through. Critics also point out that even if a wormhole were stable, it might not be traversable. The intense gravitational forces, the extreme radiation, and the potential presence of exotic matter could create a hazardous environment for any traveler. Is it possible that the journey through a wormhole would be so perilous that it would be suicidal? Or could this only allow the passing of subatomic particles and energy? This means no exploration. It's also important to remember that our understanding of wormholes is based on theoretical calculations, on solutions to Einstein's equations. But these equations are based on certain assumptions, on simplified models of the universe. What if these assumptions are wrong? What if there are aspects of space-time that we don't yet understand, aspects that could render wormholes impossible? It is true that our theoretical equations predict wormholes, but that doesn't mean they will actually be able to exist in real life. We still need to test them to confirm that theory can become a physical reality. The skeptics' arguments are not meant to discourage exploration or stifle scientific curiosity. Rather, they serve as a vital check, a reminder of the immense challenges that lie ahead and of the need for rigorous evidence and careful analysis. It's a call for more research, more experimentation, and a deeper understanding of the fundamental laws of the universe. Perhaps these theoretical equations are the problem, and we must find a new way to describe space and time. Perhaps the universe has its own way of ensuring that we don't tamper with forces that we don't fully understand. Perhaps there are limits to what we can achieve, boundaries that we can never cross. And even as the dream of wormhole travel flickers in our imaginations, it is essential to keep our feet firmly planted on the ground, guided by scientific rigor and a healthy dose of skepticism. With these issues to consider, are there any clues or discoveries that are emerging that might change the paradigm? But even as the dream of wormhole travel flickers in our imaginations, it is essential to keep our feet firmly planted on the ground, guided by scientific rigor and a healthy dose of skepticism. With these issues to consider, are there any clues or discoveries that are emerging that might change the paradigm? Perhaps the most crucial element in the entire wormhole narrative is often overlooked: the human element. The story isn't just about exotic matter and warped space-time. It's about the individuals, the pioneers who dared to dream of shortcuts through the cosmos, those who poured their intellect, their passion, and often their entire careers into unraveling these cosmic enigmas. So who are these architects of the imagination, these tireless explorers of the theoretical landscape? One name resonates above all others in the field of wormhole physics: Kip Thorne. A theoretical physicist at the California Institute of Technology, Thorne's journey into the world of wormholes began not with a dry academic exercise, but with a challenge from a friend, none other than Carl Sagan. When Sagan was writing his novel Contact, he needed someone to help him with the science and someone to tell him if it could be possible. Thorne took on the challenge, and what started as a scientific consultation became a lifelong obsession, transforming Thorne into one of the leading figures in wormhole research. Thorne's major contribution wasn't just popularizing the idea of wormholes. It was in providing a rigorous theoretical framework for their existence. He, along with his student Michael Morris, developed the concept of the Morris-Thorne wormhole, a model of a traversable wormhole that, while requiring exotic matter, offered a plausible pathway for interstellar travel. What was it about Thorne that made him so uniquely suited to tackle the complexities of wormhole physics? Was it his deep understanding of Einstein's general theory of relativity, his willingness to challenge conventional wisdom, or his unwavering belief in the power of human ingenuity? Perhaps it was a combination of all three. But Thorne wasn't working in isolation. The field of wormhole physics is a collaborative endeavor, a tapestry woven from the contributions of countless scientists around the globe. Another prominent figure in this story is Matt Visser. A physicist at Victoria University of Wellington in New Zealand, Visser has made significant contributions to our understanding of wormhole geometry, stability, and traversability. What sets Visser apart is his meticulous approach, his willingness to challenge existing assumptions, and his ability to identify subtle flaws in theoretical models. He is the kind of scientist who leaves no stone unturned, who insists on rigorous proof before accepting any new idea. Visser is also known for his work on exotic matter, exploring the properties that it would need to possess to stabilize a wormhole, and investigating potential candidates for this elusive substance. He is a kind of cosmic detective, searching for clues in the vastness of theoretical physics, piecing together the puzzle of wormholes one meticulous calculation at a time. These scientists are not just names on a research paper. They are individuals with their own unique stories, their own motivations, and their own personal struggles. What drove Thorne to dedicate his career to wormhole physics? What were the challenges he faced, the setbacks he overcame, and the moments of exhilaration that kept him going? And what about Visser? What sparked his interest in wormholes? What were the key breakthroughs that shaped his thinking, and what are the questions that continue to drive his research today? Perhaps by understanding the personal journeys of these pioneers, we can gain a deeper appreciation for the science itself. We can recognize that science is not just about equations and experiments. It's about human curiosity, about the desire to understand the universe and our place within it. Consider this. Even the most abstract scientific theories are born from human inspiration, from the spark of an idea that ignites the imagination and sets a scientist on a path of discovery. Kip Thorne, Matt Visser, and countless other researchers have not only advanced our theoretical understanding of wormholes, but also reminded us that science is ultimately a human endeavor. We should recognize the human element that has driven scientific exploration throughout the history of mankind. Science is just not about the math, theories, and equations, but scientists who all have their own personal stories. What discoveries will be made in the future that will propel this scientific idea into something real? But as inspiring as the stories of Thorne and Visser may be, And as much as science fiction may ignite our imaginations, the true destiny of wormhole research hinges on something far more profound, the future of physics itself. Are we on the verge of a scientific revolution that could unlock the secrets of space-time, or are we destined to remain forever on the shores of the unknown, gazing across an unbridgeable ocean? Imagine a vast puzzle, a cosmic jigsaw with pieces scattered across the landscape of theoretical physics. String theory, loop quantum gravity, and other unified theories represent our most ambitious attempts to assemble that puzzle, to create a single, coherent picture of the universe that encompasses everything from the smallest subatomic particle to the largest supercluster of galaxies. Could these theories hold the key to understanding wormholes, to proving their existence, and perhaps even to harnessing their power? String theory, with its elegant vision of fundamental particles as tiny vibrating strings, offers a tantalizing glimpse beyond the standard model of particle physics. In string theory, gravity itself emerges as a fundamental force, unified with all the other forces of nature. Could string theory provide the mathematical framework needed to describe the extreme gravitational conditions within a wormhole, to understand how exotic matter might behave at the quantum level, and to stabilize these elusive tunnels through space-time? It's a long shot to be sure, but string theory offers a potential pathway to a deeper understanding of the universe, one that could revolutionize our understanding of wormholes. Then there's loop quantum gravity, a radically different approach that challenges the very foundations of Einstein's general theory of relativity. Loop quantum gravity suggests that space-time itself is not smooth and continuous, but rather granular, composed of discrete units like pixels on a computer screen. What if these tiny quantum pixels of space-time can be woven together in different ways, creating different geometries, different topologies, and perhaps even wormholes? Loop quantum gravity could provide a new perspective on the nature of space-time, one that allows for the existence of wormholes without the need for exotic matter. It is a theory that is still in its infancy, but it holds the promise of revolutionizing our understanding of gravity and the cosmos. These unified theories, while still highly speculative, represent our best hope for unlocking the secrets of quantum gravity, the elusive theory that would reconcile quantum mechanics with general relativity. Quantum gravity is the holy grail of theoretical physics, the missing piece that would complete our understanding of the universe. And if we can crack the code of quantum gravity, we might finally be able to answer the question that has captivated scientists and science fiction fans for decades. Do wormholes really exist? Perhaps a deeper understanding of quantum gravity will provide definitive answers about their existence or stability. Imagine a future where wormholes are not just theoretical possibilities, but proven realities, where interstellar travel is not just a dream, but a tangible goal. What discoveries could change everything? Perhaps future breakthroughs will unveil hidden dimensions, rewriting our understanding of space and time. Perhaps a new form of matter, beyond our wildest imaginations, will be discovered, finally providing the exotic substance needed to stabilize a wormhole. Or perhaps a brilliant young physicist, inspired by the science fiction of today, will unlock the secrets of quantum gravity, revealing the true nature of wormholes and opening the door to a new era of cosmic exploration. And though many questions remain, the pursuit of answers will undoubtedly reshape the future. But with the promise of such advancements before us, it's critical to take a step back, to assess the totality of what we've explored. We've journeyed through the theoretical landscape, delved into the bizarre realm of exotic matter, and even dared to imagine the perils of traversing a wormhole, and through it all, one question has remained. Are wormholes fact or fiction? Where do they stand on the spectrum from established physics to pure speculation? The truth, as is often the case in science, is complex. We can't definitively declare wormholes to be real, but neither can we dismiss them as mere fantasy. They occupy a strange limbo, a twilight zone between what we know and what we only suspect. The theoretical foundation for wormholes is undeniably strong. Einstein's general theory of relativity, one of the most successful and well-tested theories in physics, allows for the possibility of wormholes. The equations themselves suggest that these tunnels through spacetime can exist, but theoretical possibility is not the same as physical reality. Just because something is allowed by the laws of physics doesn't mean that it actually exists in the universe. Consider the unicorn, a creature that has captivated the human imagination for centuries. There is nothing in the laws of physics that prohibits the existence of unicorns. They are theoretically possible. And yet, despite countless searches and fervent belief, no one has ever found one. The same could be true of wormholes. The biggest problem, as we've discussed at length, is the need for exotic matter. This hypothetical substance, with its negative energy density, is the key to propping open a wormhole, to preventing it from collapsing under its own gravity. But despite decades of searching, scientists have yet to find any conclusive evidence for the existence of exotic matter in the quantities needed. Imagine trying to build a bridge without any concrete. You might have a beautiful design, you might have all the tools you need, but without the fundamental building material, the project is doomed. The same is true of wormholes. Without exotic matter, they remain a theoretical curiosity, a fascinating mathematical solution with no basis in physical reality. And even if exotic matter does exist, there's the issue of stability. Wormholes, as we've seen, are incredibly fragile structures, prone to collapsing or pinching off in a fraction of a second. How could we possibly stabilize a wormhole long enough for a spaceship to pass through, let alone for repeated trips? Some physicists have proposed ingenious solutions involving quantum effects or advanced engineering techniques, but these ideas remain highly speculative. Think of it like balancing a pencil on its tip. You might be able to do it for a brief moment, but it's inherently unstable, destined to fall over. Wormholes, without some kind of stabilizing mechanism, are like that pencil, constantly teetering on the edge of collapse. On the other hand, there's the lure of the unknown, the tantalizing possibility that wormholes might be out there, waiting to be discovered. The universe is vast and mysterious, filled with phenomena that defy our current understanding of physics. Perhaps wormholes are hiding in plain sight, lurking near black holes, or scattered throughout the quantum foam of spacetime. Imagine exploring a vast, uncharted ocean. You might spend years searching without finding anything of interest, but then one day you stumble upon an undiscovered island, a hidden paradise teeming with life and wonder. The same could be true of the search for wormholes. We might search for decades without success, but then, one day, we might make a breakthrough that changes everything. Perhaps future advancements in fundamental physics, such as string theory or loop quantum gravity, will provide definitive answers about their existence or finally confirm wormholes' stability. Perhaps observations made with increasingly powerful telescopes will reveal telltale signs of wormholes, gravitational lensing patterns, or unusual radiation emissions that can no longer be explained by our current understanding of the universe. For now, the question of whether wormholes are fact or fiction remains unanswered. They stand at the boundary of our knowledge, a challenge to our ingenuity, and a testament to our enduring curiosity. Based on our current scientific understanding, wormholes are a compelling theoretical construct, but lack definitive observational evidence, which pushes them more toward speculation than established physics. But what is it that motivates us to keep searching? Even with these uncertainties looming large, even with the daunting scientific and technological hurdles we've explored, the allure of wormholes endures. Why? What is it about these theoretical tunnels that continues to grip our imaginations, fueling scientific research and inspiring countless works of science fiction? Is it simply the promise of faster-than-light travel, the tantalizing prospect of reaching distant stars within a human lifetime? Or is there something deeper at play, something that speaks to our fundamental nature as explorers, as dreamers, as beings driven by an insatiable curiosity? Perhaps it is the human drive to solve the impossible, to create something out of nothing. Like the great pyramids of Egypt, like the moon landing, Wormholes represent the ultimate challenge, a testament to our ability to overcome seemingly insurmountable obstacles. Is it simply about reaching another star system? Or is there something more meaningful in the striving itself, in the relentless pursuit of knowledge, regardless of the outcome? Consider the stories of the great explorers of the past. Magellan, Columbus, Armstrong, each driven by a desire to see what lies beyond the horizon, to chart the unknown, to push the boundaries of human exploration. They faced hardship, danger, and the very real possibility of failure, yet they persevered, driven by an unwavering belief in the power of discovery. Are we any different today? Is the allure of wormholes simply a modern manifestation of that same primal urge, that same deep-seated desire to explore the unknown? Perhaps wormholes have an enduring appeal to the stories that can be told. From a storytelling perspective, this theoretical gateway has provided writers, directors, and even game developers with the ultimate mechanism to create worlds, scenarios, and characters that can captivate the audience. The what-ifs and maybes become the ultimate hook for audiences to dive in and become invested in the outcome. Maybe it's not just about the science, maybe it's not just about the storytelling, but about us and what we represent as a species. We humans have always wondered about the stars, about the universe, about everything that is beyond our world. Wormholes serve as a way to get to know what's out there, what lies in the other planets, what lies in the other galaxies. Let's face it, it's really all about the journey, no matter how long it will take. No matter how many scientists or storytellers it may require, humans will continue to push these boundaries because it is what they do. The question is not whether we will ever achieve wormhole travel, but how the quest for this goal will transform us along the way. What new technologies will be developed? What new insights will be gained? And what new understanding of the universe will we uncover? The exploration will continue as humanity tries to understand how the universe works.